Give it the old college try. So this is question 8.39 from the textbook. And it gives us some practice on our reactions. And we'll start with the first one. So A, we're starting with this terminal alkene here. And are we doing a Markovnikov or an anti-Markovnikov addition of water here? Because we're adding, right, we're adding H2O. Could anybody tell me, is this Markovnikov or anti-Markovnikov? This be Markovnikov or so this is Markovnikov, isn't it, right? So this is a Markovnikov addition. And the thing is, you know, for Markovnikov addition, you might be thinking, well, I'll just use H3O plus, right? So let me just write an abridged version of the mechanism here. So if we just used H3O plus, that would give us this secondary carbocation. But the problem with this secondary carbocation is that we can get a rearrangement here, can't we, right? We can end up doing a rearrangement. And remember, if we can do a rearrangement, we're going to do a rearrangement. And so we would end up with this tertiary carbocation. And after our nucleophilic attack and proton transfer, we'd end up with a tertiary alcohol. So we can't use aqueous acid to do this reaction. So could anybody suggest a better set of conditions to do this reaction? What would I use to do this reaction? I'm getting, yes, exactly. Oxymercuration, demercuration is what I'm going to use. Let me just, there we go. So I'm going to use oxymercuration, demercuration. So the first step is going to be mercuric acetate and water. And the second step is going to be sodium borohydride. All right, and we do that to avoid carbocation rearrangements. All right, we got A finished. Let's take a look at B. So in B, we're doing an E2 reaction. And we actually have two types of beta protons here. We have the beta proton, which would lead to the desired product. So we have that beta proton. And then we have another beta proton here, another type of beta proton, I should say, here. And if we eliminated that, we would end up with this compound. But we're trying to make the compound in red. And so would we use a hindered base or an unhindered base to do this reaction? Could anybody help me out with this one? If we want to pull off we'd use a hindered base, wouldn't we? We'd use something like potassium T-butoxide, right? Because the butoxide ion is so big and bulky, we draw it out here, that it is going to abstract the proton in red. We form our double bond and we lose our leaving group, and we would end up with that as the major product. If we wanted to make the product in blue, we would use an unhindered base like sodium methoxide, for example. All right, so that covers that one. Let's move on to the next one. In C, am I doing a Markovnikov or an anti-Markovnikov addition of HBr in C? Exactly. So this is anti-Markovnikov addition of HBr. And so I'm going to need some hydrogen bromide. And what else do I need in here? I need an organic peroxide, exactly. And remember, that mechanism isn't covered until chapter 10, so we're good on that one. Let's move on to D. Up here. And again, this is question 8.39. So again, this is question 8.39D from Klein 4th edition. So now we have a primary alkyl halide, and we're trying to make an ether. And so if we have a primary alkyl halide, what we're going to want to do is an SN2 reaction here, right? Because we're not doing an elimination, we're doing some kind of substitution. It's not going to be an SN1, so it has to be an SN2 reaction. And the nucleophile that we would need is going to be this part of the molecule. And so for that, we would just use sodium ethoxide. So we'll put sodium ethoxide, and we'll even draw the Lewis structure of it here, partial Lewis structure, and draw the mechanism. So it's just going to be nucleophilic attack, loss of leaving group, and we're done. We've made our ether just like that. Okay, let's move on to the next one. So again, this is 8.39. In E, are we doing a Markovnikov or anti-Markovnikov addition of HCl? Right, because we're adding a hydrogen and a chlorine. This is Markovnikov addition. So Markovnikov addition of HCl. And so we could even practice drawing the mechanism of this reaction. So what's going to happen is when we treat this with HCl, the rich are going to get richer. So this carbon is richer in protons, so it's going to take the proton, and I'm going to end up with a tertiary carbocation that looks like this. And then in the last step, my chloride can come in as my nucleophile. And there's no chiral center in the final product, so we don't have to worry about that. We do a nucleophilic attack, and we get our final product, just like that. So Markovnikov addition of HCl across a double bond. Okay, the next one, is this a Markovnikov or an anti-Markovnikov addition of water across a double bond? And this one here, so exactly, this is an anti-Markovnikov, so this is anti-Markovnikov addition of water. I told you don't need to know the mechanism, but you do need to know that it's a syn addition. Okay, so syn addition, syn addition. And the reagents are going to be borane and THF, that complex in the first step. And then in the second step, we need hydrogen peroxide and sodium hydroxide. Good, anti-Markovnikov addition. All right, I think that's all I put. So let me just go back to the book. So the next one is G. We already solved G. So G, I'll put here C, B, because we already did this one in B. Let's see. And then A, B, C, D, N, G. So H, did we do H? No, we didn't do H. So let's try H. So H is where we have an exocyclic alkene. That's when the double bond comes off of the ring. And then we're doing a Markovnikov addition of HBr. And so for that one, we just need HBr and nothing else. So again, this is question 8.39. And so our reagent is going to be HBr. We can practice our mechanism, right? The rich get richer. So we draw our curved arrow through here, pull off our proton, and then we end up making a tertiary carbocation like this. And then in the last step, the bromide comes in as a nucleophile. And we do a nucleophilic attack like this. That gives us the final product. The next one, we're replacing a hydroxyl. So this is question I. So this is 8.39I. So the next one, we're replacing a tertiary alcohol with this tertiary alcohol here. And we want to convert it into a tertiary alkyl bromide. All right, a tertiary alkyl bromide. And this is a reaction that we covered earlier on. I think we only looked at it briefly, though. Does anybody remember the reagent that would affect this transformation? It's just one reagent is all you need. Anybody? Yeah, it's just HBr, right? The Beatles said love is all you need, and this reaction said all you need is HBr, right? So what happens is that you take a poor leaving group, like the hydroxyl, and you convert it to a good leaving group in the first step, okay? So we're going to get a proton transfer in the first step, and we're going to convert the hydroxyl from a crummy leaving group into a dandy leaving group, all right? And now the leaving group is going to leave. And why can it do that? Because you end up making a tertiary carbocation. It's going to look like this. And so in the last step, the bromide can come in as a nucleophile. There's no chiral center formed here. And we end up doing the nucleophilic attack and forming our final product. Good. All right, the next one is one that's going to come up a lot in organic chemistry. This is 8.39J. And so we're taking this exocyclic alkene that we saw before, this guy here, and we're just converting it to the alkane. So this would be ethyl cyclohexane. So could anybody tell me what kind of reaction conditions I would need here? So for this one, it's just a hydrogenation reaction. That's right. So all you need is hydrogen. Somebody put platinum. Savannah said platinum. We'll use that, and you could use palladium or nickel, and it will give you the same answer. And then for K, we've got this alkene here, and we want to make this compound where we have a hydroxyl pointing up, and we want to have another one pointing down like this, and it's an enantiomer. So this is an anti-dihydroxylation. So remember the steps for anti-dihydroxylation. So this is anti-dihydroxylation. Okay, so for that, we need a peroxy acid in the first step. And then in the second step, we treat that with H3O+. And that opens up the epoxide that we form. And for L, we have cyclohexene. So this compound is called not hexane, but cyclohexene. And we want to make a syn addition, syn dihydroxylation. So we want to put one hydroxyl up here and one hydroxyl up here. I told you this. So this is a meso compound. There's many ways to do this, but the most commonly used way by my students historically has been a catalytic amount of osmium tetroxide and then N-methylmorpholine and oxide as the co-oxidant. So there you go, a little bit of practice in some of the reactions that we learned. So let's take a look at the next problem, which was 8 point, give me a sec here, it was 8 point, sorry, I'm struggling with my textbook here. It was 8.42, if I'm not mistaken. Is that the one I said, 8.42? Yes. All right, so let's start with this one. And this kind of opens up a little bit of synthesis. So this is question 8.42 from Klein 4th edition. We're starting out with this compound, like this, and we have a chlorine here. We want to move the chlorine around somehow. So we want to end up with this compound. Son of a gun. I'm struggling with my Apple Pencil today. There we go. And then we're going to put the chlorine down here. All right, so we want to move the chlorine around. Well, I think the best way to solve a problem like this is to do a retrosynthesis, right? Is to go backwards and say, well, what would I need, to make this compound? And if we had this compound, so if I had a double bond here, right, like this, then all I would have to do is a Markovnikov addition of HCl to this compound, and it would give me a final product. So then we've shortened the problem, and now it's like, how do we get from here to here? Well, there's two types of beta protons, aren't there? There's these beta protons over here, and then there's this beta proton here. We want to pull off the proton in blue. If we want to pull off the proton in blue, would we use a hindered base or an unhindered base? Could anybody answer that? Yeah, you'd want to use an unhindered base, wouldn't you? So you'd use something like sodium ethoxide or sodium methoxide, and that would give you this compound where you have the double bond right where you want it, right? Because the ethoxide is going to pull off this proton, make the double bond, and you lose the leaving group like this. And now, in order to get from here to the product, all we have to do is add HCl to it, and we do a Markovnikov addition, and we're done. So it's a two-step process. First step is treat it with sodium ethoxide, and then second step is to treat it with HCl. In B, we're moving a hydroxyl group around. So we have a secondary alcohol, and we're trying to convert it into a primary alcohol. So let's just scribble this in here. So it looks something, oops. It's so hard to draw at the bottom of the iPad. There we go. All right. So new problem. Here we go. So now we're trying to go from a secondary hydroxyl to a primary hydroxyl. But again, if we did a retrosynthesis, we could say, well, all we need is this alkene, and we just do an anti-Markovnikov addition of water to that alkene, and it's going to give us the desired product. So all we need to do is form a double bond here. So how are we going to do that? Could anybody make a suggestion as to how to get from here to here to make the double bond on the end? What's the first thing I need to do is I need to convert that hydroxyl into a good leaving group because it's a crummy leaving group. How would I turn the hydroxyl into a good leaving group? Anybody have an idea about that one? Okay, well, what if I made it into a tosylate? Yes, thanks, Savannah. Exactly. So if I converted it into a tosylate, right, so if I used tosyl chloride and pyridine, then I would make a tosylate, and then I could remove this proton, right? I've got two beta protons, but I can remove the red one by using a hindered base, like potassium T-butoxide, and that's going to give me that alkene that I wanted. And then to do an anti-Markovnikov addition of water, I just treat it with borane and THF, followed by hydrogen peroxide and sodium hydroxide. Done. Done like dinner. Okay. Let's try one more maybe, and then we'll call it a day after that. That's quite a bit of synthesis. So let's try C. So in C, let us see what's going on in C. So again, this is question 8.42. And in C, we're taking a secondary alkyl halide of this compound, and we're converting it into a primary alcohol. I don't know what's up with my Apple Pencil. So let's see here. It's going to look something like this. No, I'm missing a carbon. There we go. All right, so here we go. So again, if we did a retrosynthesis, we could say, well, I can make this primary alcohol if I have this alkene. Right? As long as I have this alkene, I can just do an anti-Markovnikov addition of water, and I'm done. So we've got this beta proton over here, and then we have this beta proton over here in red. If I want to pull off the beta proton in blue, what would I use, a hindered base or an unhindered base? It's going to be a hindered base, isn't it, right? So I would use something like potassium T-butoxide, and that's going to give me the alkene that I want. And then to do the anti-Markovnikov addition of water, I'm going to use borane, THF, followed by hydrogen peroxide and sodium hydroxide. All right, so that's C. And then we could do one more. We'll do 8.42D. So 8.42, and this is question D. So where you're taking this this tertiary alcohol, and you want to make this compound. All right, plus it's an enantiomer, but in terms of retrosynthesis, you'd want to make it from this compound, right? You'd want to make it from 1-methylcyclohexene and just do an anti-Markovnikov addition of water. So then if you want to take the alcohol and make the most substituted alkene, you can do my favorite reaction in organic chemistry, which is this one, where you just treat it with sulfuric acid and you cook it up, and that's going to make the most substituted alkene. You could also make a tosylate and then treat it with an unhindered base. That will work too. There you go. And then all you have to do is do a hydroboration oxidation. Hydroboration, oxidation, and you're done. Now, again, if you did this, if you said, step 1, I'll make a tosylate with tosyl chloride and pyridine. Step 2, I'll use an unhindered base to make the Zaitsev alkene. And then step 3, I'll use borane and THF. And in step 4, I'll use hydrogen peroxide and sodium hydroxide. That will work too. I'd give that 100%. Either one is totally acceptable to do that problem.